start. I'll just make a note to everyone that I am actually recording this. So hello everybody, and welcome to our marine geoscience seminar today. Today we have Tim Minshull, who is currently spending a few months with us here at IPGP. But Tim completed his PhD at the University of Cambridge and was briefly a lecturer at the University of Birmingham. And afterwards, he's returned to full-time research at Cambridge for 8 years. Then in 1999, he moved to the University of Southampton, where he's based at the National Oceanography Centre, where he's been a full-time professor since 2004. He has diverse research interests, but in recent years, he's focused primarily on processes involved in continental breakup, seabed fluid escape structures, and the role of methane hydrates in the carbon cycle. So yeah, thanks for agreeing to talk to us today, and over to you, Tim.
Okay, so my title is Searching for the Onset of Seafloor Spreading at Rifted Margins. I'm going to try and sort of synthesize probably some work on this topic over about the last 15 years. In which I've worked with lots of other people, and I've added some of the names in the acknowledgements there, but there's lots of others too. Right, here we go. So I've talked to this slide, so I'll proceed. So I'm talking about rifted margins, and we have a sort of classification system, which probably many of you are familiar with. We talk about volcanic margins and magma pore margins, this is quite a nice diagram from Dieter Franke that sort of summarizes the characteristics of those types of margins. So magma pore margins, we see tilted fault blocks, stretched and thinned continental crust. And then we see a region where there's essentially no crust, and the mantle was exposed at the seafloor at the time of rifting. And then we see oceanic crust further seaward, and then the volcanic type, where we have lots more magmatism, so extrusive and intrusive magmatism during continental stretching, often hiding the tilted fault blocks, so they're not really imaged, and then increasing amounts of magmatic activity until we get out into oceanic crust. And there's this, on both of these, there's this region marked COT, continent-ocean transition. Actually, in the literature, there are a variety of definitions for continent-ocean transition, some of which would include a much wider region than is marked on this diagram. And then also, it has to be said, a couple other things. So this is very much a 2D perspective, and we'll see that there are some 3D margins are fully 3D, and then yeah, often the continent-ocean transition is much broader than in these cartoons. So this region of exhumed mantle might be 100 kilometers wide or more. So, and then there are some other margins that don't fit into this sort of end member classification. One that's had a lot of recent attention is the margins of the South China Sea, and there, from some recent drilling, it seems that essentially the thinned continental crust abuts against crust that's mostly igneous, so the continent-ocean transition is very narrow indeed, at most a few tens of kilometers wide. And so you can sort of classify margins around the world, and some volcanic or magma rich, some magma poor, and some intermediate. And then yeah, there are also some transform margins marked on here, which look different again. So I'm going to take us to a few different margins around the world where I've worked. So I'm going to start in the Black Sea. So the nice thing about a place like this is that the conjugate margins are close together. Perhaps a downside of it is it's quite an old rift, and because it's inside the middle of a continent with mountains around it, there's lots and lots of sediment. So everything's buried under about 8 to 10 kilometers of sediment. But the good thing is the conjugate margin is quite close to each other. So in principle, you can study both margins. So this is some work we did, the cruise was about 15 years ago. We collected some wide angle seismic data along these black lines. We had plans to do the conjugate margins, but we didn't get permission to go into this region here, which perhaps if we'd known the politics a bit better, we'd have known we'd never get permission to go in, because it's kind of disputed region between Georgia and Russia. So we collect our wide angle seismic profiles, we generate velocity models, and then we want to interpret them. And so if we want to interpret them, then we need some kind of basis to do that. And the common way we do that is by sort of comparing with other places where we think we know what the structure is and what sorts of rocks are present and whether it's continent or ocean. So this is a comparison of the velocity structure on two of these lines. So line 3, this one here in the west, and line 2, this one here in the east. On the left with an old compilation of Atlantic oceanic crust, and then on the right with some other place in the world where the crust is a bit thicker. So what we see is that the green lines, the western profile, the velocities are generally rather lower than those of oceanic crust, particularly in the lower crust. And then on the red profiles, the line in the east, the velocities are somewhat higher. The crust is rather thicker than we normally see in oceanic crust, and hence the comparison with thickened oceanic crust, and quite a good match with the velocity structure of thickened oceanic crust. So our interpretation is that we have stretched continental crust in the west, and we have thickened oceanic crust in the east. And then we had our straight line down the middle of the basin, so we could sort of link these two lines up, and we could see where the change occurred. And so I guess we looked at this, and so we see this sort of orange higher velocity material present in the east and not in the west. So this is our thickened oceanic crust, and then there seems to be this rather abrupt change. The crust gets abruptly thinner. So based on this work, we identified the limit of oceanic crust in this basin as about here. And then in which case this line 3 wouldn't have sampled the ocean at all. And then line 3, yeah, there is a sort of volcanic continent-ocean transition at the landward end of that profile. So that was work we did some time ago. More recently, we got access to some nice industry data collected with a 10-kilometer streamer. And here the multi-channel lines, the sort of bold ones are the ones with the 10-kilometer streamer. We did have a few other lines that we'd sort of collected over the years, which are the thinner ones, which went into this interpretation as well. And then they're put on top of the magnetic anomaly map. And you can see that there are some quite large magnetic anomalies. There are igneous rocks around, at the surface around the basin, in the arc to the south, and then some that have been sampled on Shatsky Ridge here. So there are some large magnetic anomalies, and then there's this kind of sort of linear magnetic anomaly in the eastern basin. Oh no. Do this to me. I'm going to see if I can escape from this. It's not letting me advance. So let's see if I can. Okay, I can advance like that. Let's see what happens. So with these reflection data, they nicely image the sort of different parts of the basin. So the stretched continent in the west, and then the ocean basin in the east, and so you can sort of relate that sequence going from west to east to a sequence of opening over time, because we can imagine that in the east, before we opened the ocean basin, maybe we had these earlier stages of rifting and continental crustal thinning. So it seems these reflection data give us quite a nice insight into how this basin opened. And then one of the things we did with these data, so basically the 10-kilometre streamer allowed us to image, or allows imaging to the bottom of these thick sediments and some of the features in the crust below, whereas before that was really impossible with the sort of 20-year-old reflection data with shorter streamers. You couldn't see the top of basement really. So we defined some basement domains based on reflection data, essentially based on the sort of morphology of the basement. And then there's, and we have three domains. Domain one is the sort of clearly continental domain with tilted fault blocks and some evidence in the sediments of sort of growth in the hanging walls of those faults. Domain two, we're not seeing those tilted fault blocks, but we're still seeing quite a bumpy basement. And then domain three, where the basement is generally quite flat and smooth, but it has these occasional steep offsets. Okay, so here's a map of what comes out of that sort of domain analysis. And then that leads into some interpretation of what those domains might be. And on top of this map, also these coloured lines are our interpretation from the wide-angle seismic data. So before we had the reflection data available to us. So domain one has the tilted fault blocks. We interpret that as continental. That's fairly straightforward. Domain three has pretty smooth basement, has a velocity structure that as we've seen looks like thickened oceanic crust. It has this one linear magnetic anomaly, and there's no sign of any syn rift sediments, no sign of anything being tilted by faulting post deposition. It's all very flat. So we interpret this as oceanic, and being sort of flat and smooth, maybe as fast spreading oceanic. I mean, we have no constraints at all on the extension rate here. And then domain two has, as we've seen, thin crust, but and velocities that we interpreted previously as continental, but it has a distinct basement morphology, and it has a magnetic character a bit different to that of domain three. And this domain two is quite narrow. So where does that leave us? So the issue this raises is that we previously on our based on our velocity models alone interpreted this region here as oceanic, but sorry, we interpreted this region as continental, but in terms of the basement morphology, in terms of the magnetic character, it looks very much like oceanic. So how can we reconcile these different ideas? Well, so let's go back in a bit more detail to the profile along the axis of the basin. And what you see is the crust gets thinner and then it gets thicker again. And actually we do have some of these higher sort of orange velocities further west, and our domain boundary is here. So seems to be at this sort of second thinning of the crust rather than at this first sort of thinning here. So a revised interpretation that accounts for kind of all of these data would be to say, well, actually this material in here that we'd interpreted as continental, well, perhaps it's not continental, perhaps this is just a much thinner oceanic layer. Perhaps we've removed most of layer three, And we do see in the ocean basins where we thin the crust, or where the crust is thinner, often it's layer 3 that's thinned preferentially. And then this this location here, where the crust thins, does seem to coincide with one of these basement steps, which could be a transform fault or a fracture zone now, the remnants of an old transform fault. So our interpretation finally then involves sort of thickened crust up against the transform faults, and then an abrupt change in an abrupt to long axis change in crustal thickness that's to do with perhaps ponding of melt against those transforms. Moving around the world briefly, I'm going to take Porcupine Basin. So this is another sort of, you might call it a failed rift, or it's a rift that's not gone very far. There's not a big ocean here. And this is a magma pore example. So not much evidence for synrift magmatism here. In the magma pore case, we also have some, we need some kind of reference to decide what we're looking at. So this is a compilation I made a few years ago of velocity models from places that had been interpreted as involving essentially mantle exhumation. And so these are the individual profiles, and then this is sort of mean and deviation from profiles two sides of the Atlantic. What we see is that you reach velocities greater than 7 kilometers per second at quite shallow depths, about 2 to 4 kilometers below basement. And then we see rather limited or sometimes no evidence for a MOHO discontinuity. A lot of these profiles have a little discontinuity in the velocity model. That's just to do with the way the velocity model has been parameterized. And in most cases, there isn't any evidence for a wide angle reflection from that discontinuity. So these are areas where we think that there's essentially direct contact between the mantle and sediments. But of course, you can have a thin crustal layer, a thin layer of continental crust above mantle that is sort of serpentinized in the same way and has its velocity having similar values to those in these profiles. So here's our set of profiles, velocity models across the axis of this basin. So again, we're seeing this transition as we go, in this case, from north to south, greater degrees of extension, greater thinning. So, but even in our northernmost profile, we do see some evidence for a reduction of velocities in the mantle underneath the thinned crust. The crust is just a few kilometers thick here, and we interpret these sort of orange colors as serpentinized mantle. We go south, the crust is a bit thinner still. Further south still, and there's hardly any crust left. The crust is just maybe 1 or 2 kilometers thick, or maybe not be present at all, right in the middle of the basin here. And there's a bit of asymmetry here. And then our southernmost profile, we see something rather different. So we see higher velocities. We do see a PMP. We see an oceanic MOHO. And so we seem to have, and the crust is much thicker, we seem to have oceanic crust in the south. So our interpretation here, a little bit similar, I guess, but this is a place where we don't have much magmatism, or any magmatism at all, perhaps, in the stretched continental part. And then we have some oceanic crust in the south. There is some old data from the 1970s further south still that really makes it look rather continental. So this little bit of oceanic crust may not may not be very laterally extensive. Moving elsewhere in the world, so we go to the Iberia-Abyssal Plain, the southern Iberia-Abyssal Plain. So the West Iberia margin is the kind of most studied of these magma pore margins. We did a lot of work about 20 years ago there, or no, even more than that actually, more than 20 years ago. I revisited this data set a little bit a few years ago. So this is, yeah, here's again a set of wide angle seismic profiles with coincident reflection profiles. And to give you some context here, so the continent's over here. This J anomaly is something that there's a bit of controversy about. It's a linear magnetic anomaly, unclear exactly what it is. And then there was quite a bit of drilling on this margin to support what we can do with the geophysics. So this is a magnetization inversion from this area, and the interpretation here was that this J anomaly corresponds to Mesozoic anomaly M3, and then there's maybe even some older Mesozoic anomalies, this sort of weakly linear thing here. So J sort of looks a bit like a linear seafloor spreading anomaly. This was what came out of sort of revisiting the velocities. So this was the model we published in the year 2000. This is the 2014 model. It's very, very similar, and it just has this is the oceanic crust, and then sorry, the color scheme is a bit different here. The purpley stuff is the sort of serpentinized mantle with velocities above 7. Oceanic crust here, and then we've just pushed the limits of oceanic crust a bit further seaward. And as we recognise in this paper, the data don't give strong reasons to distinguish between these two models. But this model with the and part of the problem is that we lost a few instruments in here, so there's a 60-kilometre gap between instruments that we have data from. So it's all pretty poorly resolved in here. And if we make this boundary a bit further west, then we're a bit more consistent with both an old crossing profile from the 1980s, this line 3, and also with the results of the drilling, which is not on this profile, it's further north, but the drilling didn't find anything, didn't find oceanic basalts, found some intrusive mafic igneous rocks, but something that didn't really look like oceanic crust. And then it's also consistent with the conjugate margin. So I've turned this around, so east is on the left and west on the east now. And so I've lined them up at this interpreted M3 or J anomaly. And then what you see is the J anomaly is on both sides, perhaps above the stuff that's exhumed mantle, and then maybe oceanic crust is further seaward. You can see the spacing between the anomalies as interpreted is different on the two margins. So there was asymmetric spreading. And then there's this big seamount at the western end of the Iberian margin profile. So oceanic crust is thickened there, and that may be something to do with the Madeira hotspot rather than being anything to do with breakup processes as such. But yeah, there are alternative interpretations of this profile. So Bronner et al. In Nature Geoscience published some work where they modeled the magnetic anomalies, and they said, well, this could equally be, there could be more serpentinized mantle here. There could be just some basalts on top, and then this change in velocities could just be due to some underplating of that serpentinite by magmatism. And so maybe this J anomaly is nothing to do with seafloor spreading. It's just kind of a burst of magmatism, and the real ocean is way out further west. So, and with available data, it's difficult to resolve between those two rather different models. Let's go a bit further north. So this is the deep glacier margin. So it's it's only 100 kilometers or so to the north of the area I just showed you. So characteristics. This is again a well-studied area. There's this well-imaged detachment fault above which the faults, the normal faults on the margin seem to be detaching. And then the other characteristic of this margin is this prototype ridge, which is imaged was imaged a long time ago. Lots of work by French scientists here back in the 70s and 80s. Showing that this ridge extends over long distances, and there may be several of these prototype ridges. So we have done lots of work on the S detachment and what's above it, but I'm not going to talk about that. I'm going to focus on what's further out towards the ocean. So, I mean, this wasn't in our proposal, but we decided, since we were going there, that as well as doing our 3D survey, we'd just go and have a look and see if we could find where was the ocean if we headed out further west, because basically the existing data didn't tell us where the ocean was. It kind of ended at the prototype ridge. This is a magnetic anomaly map, and the J anomaly here kind of just fizzles out south of this area. So whether or not one thinks that the J anomaly is anything to do with seafloor spreading, it's just not present here. So we've got no magnetic evidence to tell us that we're out in the ocean until way out here, where we get to anomaly 34. So we couldn't go out as far as anomaly 34, that was just too far away, but we went about 60 kilometers further out in terms of instrument spacing, a bit further in terms of shooting. So what did we find? Well, yeah, we didn't really find the ocean. What we found was essentially a velocity that increased rather rapidly with depth, so reaching these velocities above 7, perhaps. I mean, the sort of darker blue is the sediment here, and then these paler colours, you're into basement, and you reach the 7 kilometers per second contour within 2 or 3 kilometers of the top of basement. We didn't really find something that looks like a conventional PMP, but we did find a reflector that's quite a strong reflector, so could be the base of the crust. But just at 1 to 2 kilometers below the top of basement, so very shallow. So interpretation of this area is that this is more exhumed mantle. I mean, we know the prototype ridge has been sampled, so it's mantle. Some more exhumed mantle out here, and there might be, I mean, there are bits of something else, thin pieces of something else, which could be thin basaltic crust. I mean, I think we can't really tell what it is exactly. All we see is that there's a discontinuity, so there's something different at the top. There's a whole series of these ridges, so maybe all these ridges are like prototype ridges. And wherever normal oceanic crust is, well, it's kind of further west of this profile. So to summarize those observations, continent ocean transitions can be narrow or can be quite wide. We can learn quite a lot from fail drifts, and they sort of tell us, I mean, we can sort of unpick evolution through time if we assume that we've got, if we look at different degrees of extension, that's sort of corresponding to different stages of rifting. And they can sort of tell us quite a bit about the 3D evolution of rifted margins. Something we've known for a long time is that at magma pore margins, we get a broad region of basement where there's little or no crust. And there may be linear magnetic anomalies, or at least elongated magnetic anomalies. And so probably there is some extrusive or intrusive magnetism in these regions. but not enough to provide a continuous layer. I mean, somewhere in this region where the mantle exhumed, we're probably transitioning from exhumed subcontinental lithospheric mantle to oceanic mantle that's formed by cooling of the asthenosphere, but it's kind of quite difficult, certainly with seismic velocity models, quite difficult to say where that might be. And then at the West Iberia margin, which is the place where the magma pore margin has been the focus of really the most study, well, we can't really say where the seaward limit of the continent-ocean transition is, and therefore what that limit looks like. We don't have enough data. Now, there is some recent work that's been done on that problem, which by other groups that hopefully will shed more light on that question. To finish off, I'm sort of going to take us to a future experiment, and talk a bit about the role of electromagnetic methods. So, I mean, one of the problems we have with our seismic experiments is that mafic crustal rocks and serpentinized mantle rocks have quite similar velocities. This is an old compilation, so P wave velocity along the bottom, shear wave velocity along the top. You know, the P wave velocities overlap very much so. So if you have a velocity between about 5 kilometers per second and about 8 kilometers per second, well, it could be serpentinite with various degrees of serpentinization, or it could be mafic igneous rocks. And if you only have the P wave velocity, well, we kind of look at how velocity varies with depth, and that tells us quite a lot. But you have some difficulties. If you have S-wave velocity information, that adds quite a lot. And you know, there is a different trend in the S-wave, in the VPVS for the serpentinites and for the mafic igneous rocks. So you can potentially distinguish. I mean, if you're in this region here, it still gets pretty difficult because the fields are overlapping, even if the trends are different. And then, of course, we don't generate S-waves with our marine seismic sources, so we have to rely on mode conversion to see them. And one of the problems at rifted margins is, so to get mode conversion, you need a strong contrast in velocities at the top of basement, or normally at the top of basement. Because rifted margins tend to be covered by thick sediments, and sediments increase their velocities as they compact, often we don't have that strong contrast, so we don't record S waves. We just don't see them. I mean, they may be there, but if they're there, they're very weak, low amplitude. So electromagnetics might have a role because they tell us about resistivity. Mafic igneous rocks, or particularly gabbros, tend to be really rather resistive, whereas serpentinites tend to be a lot less resistive, primarily because they're more porous and permeable. So that difference may be an order of magnitude or so. And then modern controlled source electromagnetic experiments can allow us to detect changes in fluid content in the crust and upper mantle on length scales of a few kilometers or less. So this is some work by the Scripps group on a convergent margin where they're showing, so these are the flexural bending faults, and they're showing that they see velocity contrasts associated with those faults that they attribute to changes in porosity primarily. So we can see that with electromagnetic methods, and then there's also some evidence that we might see some differences in the electrical properties between continental lithospheric mantle and oceanic mantle. So the top transect here, and just look at this top part, this is sort of more crustal view down here. But if we look at this sort of mantle view, so cratonic continental lithosphere here has really very high resistivities, and then when we get out into the oceanic lithosphere, The resistivities are still high, but they're much lower. So there may be a difference in resistivity. This is some work on the eastern margin of North America. Here we're not looking at resistivity, here we're looking at anisotropy of resistivity. So that's something that, so this is the ratio between the vertical and the horizontal resistivity. And that's something that comes out kind of as standard if you're inverting both magnetotelluric and control source electromagnetic profiles. You can do this, and what this work showed was that there was a difference in anisotropy between the North American continental lithosphere and the oceanic lithosphere further seaward. So there's some hope that with electromagnetic methods we might be able to get at this transition from continental to oceanic mantle. So this is the future experiment. My slide until recently said likely summer 2022, but due to some problems with vessels, everything's been delayed. So we hope to do this in summer 2023. This is the margin southwest of the UK, so to the west of Brittany. And this is a joint seismic and electromagnetic experiment, which will be fairly densely sampled. So the nice thing here is we can go from what we know is continental crust over here. I mean, it's been drilled out to all the way to anomaly 34, which I think, yeah, if anomaly 34 isn't a seafloor spreading magnetic anomaly, then I guess we're in trouble with lots of our understanding of how these anomalies are formed. So hopefully we really are out in the ocean if we've got as far as anomaly 34, and then we can have a look at what's in between. And we do have a bit of information on what's in between from some work we did, again, about 20 years ago. So here, the sediment's rather thin. So there are actually, you do actually record S waves if you put down ocean bottom seismometers. And based on those P and S wave velocities, we interpret that there is a region here of exhumed mantle. It's a different case from the West Iberia margin because there is some magnetism. There is this basaltic body which was drilled just right at the edge of the thin continent. But this region out here, so the basement has low relief, there's no MOHO reflections, and the VP-VS ratio is quite high. So all of these things suggest that we're not dealing with normal slow spreading oceanic crust here. We've probably got some mantle exhumation. So, and then actually, since we did that work, there's some recent work done by the Irish government. They've collected lots of seismic reflection profiles. We've got a little bit more reflection data from a cruise actually this summer, which was testing the airgun source. So it was just a test cruise, but since this is the nearest bit of international waters to Southampton, this is a convenient place to go to do that. So you see, yeah, so the basement isn't always flat, but the sediments are always quite thin. So maximum thickness, I mean, these are time sections, here's the vertical scale. So the sediments aren't more than about 1 second thick or one kilometer thick. And that's good for electromagnetics. So conductive layers attenuate the signal quite strongly. So if you have thick oceanic sediments, control source electromagnetics is going to struggle, but we've got rather little here. So to finish, yeah, so there's much that's still unclear about how seafloor spreading really starts at magma pore rich rifted margins, and we need profiles that go further seaward than the ones we've collected in the past. And then I think electromagnetic techniques have much to offer, particularly where the sediment cover is thin. So I'll finish there. Thank you. Thank you for listening.
Okay, thanks for that, Tim. That was a very interesting talk. So if anybody has any questions, just put a little note in the chat to say that you have a question, and then I guess I can just unmute you and you can ask the question. Or you could just type your question in the chat and I can read it out if you'd rather. Natalie has a question. Oh, bear with me.
Hi, team. Thank you for this next talk. This is the first of the year in mind science, the first of the academic year. So I have a question on your techniques, electromagnetic technique. You have shown a figure with a asthenosphere rise. It's the work from Adam et al.
This one.
Yes. So are you able to image the very deep things, or may
So with controlled source electromagnetics, we're only going to see 3 or 4 kilometers beneath basement. So the high resolution imaging will be restricted to sort of what you might think of as crustal levels, whether or not there is any crust. But we are doing, we will do a magnetotelluric experiment, and this is a magnetotelluric experiment. And with magnetotellurics, you can image quite deep. How deep depends on a number of things, but typically, well, you can see the vertical scales on here. So the top image, they cut it off at 60 kilometers, but the bottom one is cut off at 250. What you can get depends on a number of things. It depends on the duration of the deployment, and it depends also on the depth of the ocean. Essentially, the deeper the ocean, the lower your frequency cutoff is in terms of the top end, which limits your resolution. So, if the ocean is shallow, you get better resolution. If the ocean is deep, your resolution becomes poorer. And then if you have a long deployment, you can look deeper. If you have a short deployment, you can't look quite as deep.
Okay.
Okay, I have a very sort of simple question, Tim. Is there any way like surface data could help to constrain this? And obviously you have the sediments, but I mean, like oceanic crust has a very sort of obvious surface expression, and then the continent has a, continental margins have their own sort of unique surface expression as well. I was wondering if there's any sort of consistency in the bit in between that you might be able to use to help constrain what's happening below as well, or if anyone's tried to study it at all.
So there has been some work on that. Yes, I mean, obviously in terms of surface, I mean, everything tends to be covered with flat-lying mud. But of course, if you've got good seismic reflection data, you can strip that off, and then you can look at the basement morphology, and that does tell you something. And there's a nice paper by Daniel Solti a few years ago where he looks at sort of basement roughness at a variety of margins around the world. I think probably the issue is that we don't, if you're going to use basement roughness to determine what the basement is, then you need quite a good database of what different sorts of basement look like. And I'm not sure we yet really have that database in places where we really know, because of course if it's covered in mud, then we only really know what we've got if we've drilled it. What we see with the exhumed mantle is that sometimes it's this kind of flat and smooth basement, and sometimes we get these peridotite ridges. And I guess at mid-ocean ridges we get similar variations in in morphology. There are places that are flat and smooth, and there are places that are where, you know, where there is mantle exhumed, or well, there's no crust, so the seabed is pentonite. There's places where it's flat and smooth, and there's places where it's you know, there are big normal faults, and it's not flat and smooth. So I think there are some prospects for using basement morphology, but it's quite difficult.
Yeah. Satish, do you want to go ahead?
Yes, thank you very much, Tim. Sorry, I missed your most of the talk. My question is coming back to the boundary between serpentinization and the perovskite. Can you really distinguish between these two boundaries, serpentinization and perovskite, or the moho, or whatever you want to call it? Have you ever seen any evidence of boundary between these two?
So that's a good question. Nice to see you, Satish. So mostly in these areas of exhumed mantle, what we don't really see a boundary. So we just see velocity increasing smoothly with depth until, you know, you get beyond where we have any information. And then I guess, you know, with our control source seismic data, the depth that we get to varies a bit, but I guess usually, yeah, or very often, let's say, we can reach velocities of 8 kilometers per second, where we'd say there isn't serpentinization. But what happens, I mean, what we don't see very often is, so normally we just see a smooth velocity increase with depth. Occasionally, we do see something that looks like a moho reflection. It's usually weaker. We really very rarely see it in reflection data, but we might see a weak wide angle reflection. And so, for example, in our old Goban Spur data set, we did see that a little bit. And so our model, this one here, it does have a boundary. Yeah, I think those black lines are where we saw reflectors. That boundary, of course, is in, you know, is between velocities that are above 7 above it and, you know, just a little bit higher below it. So there's not a big velocity contrast. So I think we don't know much about that boundary. I mean, there are these concepts that you might have a serpentinization front and something rather abrupt. Perhaps that's present in some places. Perhaps we don't have good enough data to see where it is, but we don't really see such a boundary very often.
Thank you.
Okay, does anyone else have any questions? No. Okay, good. Well, great. Thanks for that, Tim. And yes, as I say, I've recorded this talk, so I will put it up on the YouTube channel this afternoon at some point or later on for people who missed it. But yeah, okay, thanks for that again, Tim, and see you all next time, everybody.
Yeah. Perhaps you can edit out the.
Yes. Yes.
Bye. Bye.
Give it a
Thank you,
go.
Tim.